Hi, everyone, and hi, Dick. I'd like to say that I'm incredibly happy and honored to be here to celebrate your 80th birthday and to be among the speakers. And I met you, as you know, in '79 because I was at Berkeley from '79 to 1982. And I cannot find words to say how influential Dick was on me professionally and on all of us at Berkeley. You are an inspiration to all of us, whether we were your students or we're not your students. And I still, the community at Berkeley at the time was very close-knit, the theory community, and we used to go to lunches on Euclid to this cafe, which I think was named Café Depresso. I think that was the name. It was a bunch of us, and Manuel and Dick, and Jean Lawler sometimes, and they would talk about theory and the recent results, and Dick would ask all kinds of penetrating questions. And probably as a person in that stature, you don't realize that every word you say really falls on very acute listening ears and has a lot of impact and has a lot of significance. And I think that some questions that you asked when we showed you some mental poker protocol, Silvio and I originally, and we said that this ith bit is hidden. You said, well, what about some exclusive OR of the bits? You say, oh, yeah, that's a good question. So then we went and asked for, and worked on it. Or then we had a good mental poker protocol, and you were saying, well, maybe you have actually a way here to hide a bit. So you had these observations, which, for us, they were fundamental and very guiding. And if I had some words to describe you, I would say that you are incredibly wise, as you probably know, or maybe you don't know. Very wise, very wise. You always have this very universal view of things, even though you're a master of technique. So it's a kind of a very intriguing combination of actually seeing the big picture and yet also being also a master of detail, and you're very funny. So humor is a big thing that defines you. Somehow was not mentioned today, or at least not, but it's true. But I guess what's to mention? It's just a fact. It's so obvious. It's as if talking about Dick, you have to think of his humor. You had, in my experience, extremely open to new ideas, which I think has been always true, and certainly true when this whole cryptography thing was happening at Berkeley, and very patient, I felt. I don't know if you're patient in your personal life, but you were very patient with us, when we would come and explain all these very vague ideas, and you would listen. And I heard from Mike Sipser that you told him, maybe you don't remember this, is that it seems to be beneficial, but you have no idea what they're talking about. So thank you. Thank you very much. Okay, and I guess I want to say that Berkeley's always been a wonderful place. It still is. But for me, it will always be the place of Dick and Manuel, and that's how it is in my mind. So I'm very happy to be here. And I'm also happy to be in this session because you have been also a father figure for all of us. So I guess Jeremy follows after me, so it's kind of fitting. Now, I want to say that I'm not the only one who feels this way. So there's a few other people who've sent you the regards from MIT, Ronit, Mike Sipser, Silvio, and I have some sound here. Some of it is not working. It's not very impressive, but I'll do it anyway.
Happy birthday, Dick.
So that's Mike, and now Ronit.
Hi, Dick. Thank you for everything, for your research that defined our field, for your teaching which captivated our imagination, for your support of young graduate students, for creating a hothouse of inspiration, creativity, and excitement at Berkeley. Happy birthday.
Okay, and here is, this is Oded. For some reason sent a cat. He says he lost his voice, so, okay. And Silvio actually sent a very long speech, but it was made for IBM, and it doesn't work on my Mac, so I'll send it to you personally. Anyway, so luckily I do have a few minutes to speak myself, so, okay. So when I was invited, I was trying to decide what to talk about. And I wanted to talk about something that would interest Dick and connect up to his work. And that's shouldn't be hard because he's worked on so many fields. And I've just enumerated here the things, his contribution besides NP hardness to algorithms. Going graph algorithms of all sorts, combinatorial optimization, approximation, parallel, randomized, competitive and online, and computational biology. So what I've decided is instead of talking about any one of these, I will talk about work that in some sense is very inspired by the kind of way that many of these works evolve. So often, almost in many of his papers, as I think Aurora already mentioned earlier today, Dick says there's a problem and it's hard. It's either NP hard, or maybe there's the best algorithm that's known is NM for N vertices and M edges. And then he asks, how can we do better? So if it's an NP hard problem, what kind of distribution is over the inputs, average case distribution that will yield a polynomial time algorithm? And if it's an NM algorithm, what kind of average case distribution again would yield a linear time algorithm, and so forth. So the work that I'm going to talk about goes along, in some sense, a similar vein, except we are facing a situation where there is no worse. The worst case is, let's say, NP hard, and the average case is also very hard. Then what do you do? Okay? And we'll tell you about some work, recent work about this problem with Irit Dinur and Rachel Lin. And we call this the algorithmic benefit of correlated instances. The truth is, the name of the paper is the complexity benefit of correlated instances, but since it's your birthday, I changed it to the algorithmic benefit. And an alternative title, which I'll touch on only at the end, is why do we spend time actually talking to each other? I mean, it's a good question. We spend a lot of time talking to each other. Is there a reason behind it, or is it just enjoyable? Which is also a good reason. But in any case, so that's what I'm going to speak about, the algorithmic benefit of correlated instances. So the idea here is what we want to study, just sort of as a prelude, is a situation where we've got a problem and it's hard. It's hard in the worst case, it's hard in the average case. What else can we do? And specifically, we're going to look at a situation where, in addition to the instance that we're trying to solve, we may have some other correlated instance available to us. How do we take advantage of these extra instances to make our problem easy? And we'll see that some situations where you take a problem which is intractable, if you just have a single instance, and if you're given some correlated instances, and I'll define what I mean by correlated instances, it will become tractable. Okay, so actually this doesn't come from the air. If we think about factoring integers, then it's a well-known hard problem. So let's say if there's a number n, product of p, q, then it's hard to find these factors, p and q. But if for some reason, it's not clear how, actually Dick, I'm going to come over here. I don't know how you can look at us and the screen at the same time, so I'm sorry. So it's not, however, if you're given another number, n prime, which is a product of the same prime, p times some other prime, q prime, it becomes really easy. You take the greatest common divisor of n and n prime, and you can factor. And actually, this type of correlation between n and n prime was recently exploited in a paper with Nadia Henninger and a lot of other people, a couple other people, where they showed that in fact, if you look at cryptographic keys over the internet, lots of them have factors in common, or they have some correlation. So they were generated with a poor pseudo-random number generator, so that the composite numbers, which were supposed to be all hard in isolation, actually had enough structure and relationship between each other so that you could actually factor them completely. Now this seems a very specialized problem. It's algebraic. Okay, it's algebraic. Someone generated it incorrectly, let's say these prime divisors. But the thesis of this work is that actually this situation is not so rare. So it's not so rare that the kind of instances that we look at and want to solve are may be correlated with each other. And we should take advantage of it whenever we can. So we want to think of correlated instances as sort of a phenomenon. In some examples, even if we don't just talk about doing fast algorithm where you have instances and you want a faster solution, we could think of it about biology, where if you want to learn the mapping from genotype to phenotype of an organism, you draw data from multiple specimens which are correlated to each other and provide you multiple correlated instances. And this is something that we can work with in order to draw conclusions. Another situation might be if you think about error correcting codes. We'd like to correct as many errors as possible, but we're not just faced necessarily with one document. We may be faced with a lot of versions of a document, all of which have errors, but they're correlated with each other. And that might help us to figure out faster or more reliably where errors occurred. And there are many, many examples of this sort that you can come up with on your own. So essentially, more generally, we would say that whenever instances are derived in some sense from a source, from a single source, we may treat them as correlated, and we try to solve them together rather than solve them apart. So here's a nice picture, which Irit drew for me, I think. And that is, on the top, there is a source. There's a bunch of instances generated from the source. Each one on its own might be difficult to solve. Come up with a solution, like from the red, pink, green, blue, whatever it might be, each one individually is easy. And we argue, why don't we look at all these instances together, not the solutions, just the instances. Possibly then it would be easier to find a solution. So there's a model here, more formally, rather than just in picture. So what is the model? So we have some sort of generating process where in the first step, what it does is, that's the ordinary algorithmic story, where you get, there's some sort of a distribution, some primary distribution, might be worst case, might be average case. And this distribution, from there comes the primary instance. So that's the usual job of an algorithmic designer. And let's call this instance I, and the solution S. Okay, so in a sense, let's think that this was generated by some process, might be worst case process, that generates the instance and the solution. And the new thing is that we want to look at other auxiliary instances. And how are they generated? They, again, there is some process, generates I1 through IT with some underlying solutions S1 through ST. And we want this distribution to depend both on the instance, the primary instance, and the primary solution. So it has been looked at. You have an instance, you perturb it, you see what happens now. We're not perturbing the instance. The generating process is aware both of the instance and the solution and creates a new distribution of instances which depends both on the solution and the instance. So when I say that we perturb, what kind of they're correlated, what kind of correlation may be interesting? That's a good question. The kind that we're going to look at this work is going to be through some small perturbation of the solution. So if you have, let's say, for example, a graph with a planted clique, you may think of perturbing the clique and looking at, that will give you the new graph. So the two cliques and the two graphs may have a large overlap. Or if you think about a system of equations, you may think of, look at the solution to the equations and perturbing the solutions. And that yields a set of new equations for which those new perturbed solutions are solutions. So why did we choose such a strange definition? For one thing, the factoring example works this way, right? So n is equal to pq, and the other n prime is equal to p times q prime. It's really, the solutions are correlated. It's not clear that it's something that would be necessarily, it's not clear how to go from n to n prime. In fact, we know that that's difficult. So we don't want the kind of perturbation that are easy to get just from the instance. Because what we'd like to get is a real speed up. Not just a polynomial speed up, but really to be able to go, let's say, from intractable to tractable. Okay, great. So the focus of this work is on constraint satisfaction problems. So we choose a particular set of problems, and we show how this model of correlated instances can yield, a speed up. So what's constraint satisfaction problems? We all know. They capture KSAT, many graph algorithms, system of sparse equations, and they're NP-hard to solve and even NP-hard to approximate. Okay, so constraint satisfaction. And also are conjectured to be hard to solve on the average. So if we look at it as a picture, so pictorially we have a graph, right? So there's a bunch of, there's a graph, these edges, these blue edges. In the top there are the input bits, in the bottom there are the output bits. And the thing about this graph is that each output node is a function of a d, small number of input nodes, so there's low locality. And then you label the output nodes depending on what that predicate p evaluated on those few locations gives you. And now the question you ask, given the graph and given a labeling of the output nodes, what's the labeling of the input nodes that yielded that labeling on the output nodes? Okay, so this is the constraint satisfaction problem we're looking at. G, the graph is known, the predicate is known, the labels on the y's are known, and what we're asking is what are the labels on the x's? So in the worst case, these things are NP-hard. Usually you think about it as if all the y's are ones, you're satisfying all the constraints, but you also allow negation, so these things are not that different from each other. But let's look also at an average case of this question. Okay, so what's an average CSP? An average CSP would go like this. So there's a description here in yellow of what it is, and that is where you choose the graph at random. Okay, so you fix the predicate, then you choose the graph at random, you choose the values of x at random, and then you compute what y is. So given that x has been chosen, the graph has been chosen at random, the predicate is fixed, you value the predicate on each one of the output labels. Now, it turns out that it's hard to find an x. We don't know how to find an x that satisfies all these constraints, or even approximate it. So this is a hard problem. In fact, Goldwasser suggested that this is a one-way function. This gives you an example of a one-way function which is hard to invert on the average. So what about correlation? So these are my primary instances. There are these CSP instances. And now I'm asking, what correlated instances may you be given so that you would use in order to solve that primary instance? So here's two models of correlation. So the first one is, as I said, given an x and a graph and a predicate and a y, computed it according to this x and y and p, take the x, take every single bit of x and flip it with some small probability, something between 0 and a half. Okay? So you perturb each bit slightly. And now this gives you a new auxiliary instance. And do this again. Perturb again, perturb again, perturb again, always the primary instance. Do it for a while. And this gives you, let's say, 1 auxiliary instance, 2, 3, as many as you need. Yes?
Is the graph the same?
The graph is the same. Good. So it would be better if the graph was not the same, but it's the same. So that's one model. The second model, and the algorithmic question is still, given y and g and p, find x. Okay? But this time you're also given the y1, y2, y3. You're not given any of the x's. Another model, which seems less natural, but is going to be very important, is what I call the known difference model. In this model, not only that you're perturbed things, and now you're given the yi's, you're actually given the differences also. You're much luckier. Somebody tells you what is the difference between x and x1, x and x2, x and x3, and so forth. So they tell you these deltas. Now why, and they ask you the same question. You know what, now I gave you extra information. I gave you the x's, I gave you the deltas. Find me the primary x. So why is that reasonable? That's a good question, but I think it is very reasonable. The reason is, think about it again, if you want to think back on biology, I was motivated by Ron Shamir's talk, that sometimes you have an ability to perturb the solution. Okay? So it's not an incredible thing that you can perturb. In cryptography, it's something we call differential cryptanalysis. We call it a tampering model. So this model is not a tampering model. It's not that you can say, I want to perturb the ith variable, the jth variable, the kth variable. Somebody did this randomly, but they told you what the differences are. But more importantly, whether this is a natural model or not, is that this will be a stepping stone for us. We will see that this model is much easier to work with. And once you have a solution worked out for this model, you can show how to sort of use it as a solution for the first model, where you're not given the differences, you're just given the perturbed instances. Okay, great. So what can we show? So I know that this is just supposed to be celebratory. But since I think this paper was rejected from Fox, this is my opportunity to revenge myself. It's a good paper. Anyway, so what are the main results here? Okay? Okay. So what are the main results here? Let me just mention the three main results. There's a few others. But the first one says essentially, let's look at this random CSP. Let's look at this random perturbed solution model. What can you do? So what we show is that if you're given log n or log n extra instances, okay, you have n variables, but you're given order log n extra instances, there is an algorithm, a polynomial time efficient algorithm that finds the solution that satisfies essentially almost all the constraints. So you don't find exactly, but you find a solution that satisfies almost all the constraints. And in fact, you can show that it's pretty close to the original solution in terms of Hamming distance. Okay, so that's good. The second, but this is random CSP. What can you do in the case of worst case? So you're given the worst case graph, the worst case x, okay? Is there anything you can do? And the answer is that if you knew the differences, okay, so for example, for a second now, I'm making my life a little easier. I made it a little harder because it's the worst case instance, but I'm also gonna make it easier. So I'm gonna give you not only those perturbations, but also the differences. And it turns out in this case, we're really home free. That you can show that for any epsilon between 0 and a half, and for any density I mean how many variable constraints are there versus how many variables, you can actually find exactly a solution given order log n perturbations. Okay, so knowing the differences is a huge help. And in fact, I will even give you a hint why knowing the differences is a huge help. Moreover, the proof of the first theorem will be along the lines of first we estimate the differences, and then we apply theorem 2. So knowing the differences is really the right algorithmic machinery. First you try to find the differences between x, these perturbations, somehow estimate them, and then use them to solve your primary instance. Okay, so by the way, there's nothing here. Actually, this idea extends to locality, which is not just constant. So far, the constraint satisfaction problem just took a constant d. You can think of it as 5, 10, whatever. But it extends to low locality, so order log n. These p's, they don't always have to be the same predicate. It could be a sequence of predicates of different p1, p2 on every output node. So it's much more general. And yet, this is somewhat tight. So there is actually there are predicates p where you need, there is a constant c such as c log n is not going to be enough. Okay. Finally, so I said two things. One, the first theorem says, you know, if you have random perturbations for an average case instance, you can find the primary one, as long as you have order log n of them. The second one said, if you have the known differences, you can even do it in the worst case. And the third one says, well, what about if you're only given one single other instance? Can you do anything then? Well, it turns out that even then you can do something, but it has to be of a special class of predicates. So therefore, a special class of predicates, which in some sense are highly correlated with one of the variables that the predicate takes, you can even solve the problem using only one additional predicate, one additional perturbed instance. Okay, so some idea of why these correlations help, and then I'll almost be done. Am I supposed to be done? No, I have a couple more minutes, right? Okay, so some idea of why correlation may help. Okay, so remember the picture. The picture is that we have these x's, the reds, and then we have these blue edges that connect to the y's. And our goal is to find x. Okay, we only know the x, the y's, and the blues, right? How it connects to the x. And then somebody gives me some perturbed instance, y1, y2, y3. But I'm now showing you something that's theorem 2. We're in the good situation where somebody even told me the differences. So they even gave me the deltas. So I know. I just hope nobody talks to me because it's not good once you start talking to me. Okay, okay, whatever. So this is the situation, right? So if we sort of focus on a particular location in the y string, so that where I marked it in yellow, notice that it only depends on those 3 locations in x. Let's say the first one, I think it's the 5th and the 6th. And it might change or might not change. And furthermore, I'm told exactly what the difference in the x's were. So one kind of key observation, or one observation, I don't know if key or not, but one observation is that if you give in order log n instances, okay, then clearly you are going to, if you look at those 3 bits, you will see all possible shifts of these 3 bits. So you will see those bits plus 0, 0, 0, plus 0, 0, 1, plus 0, 1, 0, and so forth. Okay, you see all these shifts. And what that tells you is that actually this could give you an alternative, essentially encoding of x. So we're trying to find x, right? And I claim that this information leads to a very natural encoding of x, which we'll call the shift encoding. What do we mean? So another encoding of x is the value of this predicate on x plus the shift delta, okay, for all possible deltas. So for example, in this over here, you know, if the encoding of x and x prime are these columns here. So this is one column, one encoding of x, and another encoding of x. It's kind of a different encoding of x. If this encoding is unique, okay, so for some predicates, this encoding is unique. And once this encoding is unique, we're sort of done. Why is that? Because, you know, it's 2 to the d. Those are all possible shifts, okay? If I got all the 2 to the d, and it's unique, now I know exactly what x is. But unfortunately, that's not true necessarily. For some predicates, mapping is not one-to-one. And then the problem becomes harder. Not much harder. There's still enough structure here. And the structure is that essentially you can show that there's a unique linear subspace that contains the difference between x and x prime for all those x and x primes that have the same encoding. And that, in other words, means that you can write down a system of linear equations. The predicate originally wasn't linear. A system of linear equations on the bits of x, and you can solve them, because we know how to solve linear equations. Great, so this leads to an algorithm. Forget about the algorithm. Let's just go on to the next question, which is harder. And that is, what if we're not told the differences? The whole point here was that we're told the differences. Okay? What if you're not told the differences? What would you do? Well, you could hope to do the same. So you're saying, okay, so the input now is a little worse. So in other words, I'm not given these deltas. I'm just given the y's, and I want to find the x's. And as I said before, so the thing to do is to approximate the deltas. Why should you even hope that that's the line in red there, why should you even hope that you can approximate the differences? Because in some sense, if you look at the y and it's flipped, right? Then, and your y is connected, let's say, to x1, x7, x5, then you know that one of the x's is flipped. Something has changed about them. And you have, over constraints, you can take sort of a vote. You suggest sort of a natural voting procedure which would tell you whether x was changed or not, and hence, what is the delta? Okay? And in fact, that's a good idea. You could do some local, do some voting, get an approximation. Unfortunately, this is not such a good idea, or at least it's not sufficient, because then, eventually what you have a whole bunch of equations constraining x from one value of the output, and then another equation constraining x from another value of the output, and so forth. But this gives you a system of noisy linear equations. Noisy linear equations are sort of notoriously hard to deal with. We've based a lot of crypto on this, learning parity with noise, LWE, and so forth. So we're in trouble. Now we have to do something more complicated, which I will not torture you with. Okay. So what are some questions you can ask? And we did ask some of them. So one question that is very natural is, maybe it just helped us. Correlation helped us because we worked on this weird randomized CSP. So that's what we called the devil question. What does Chacham, from Passover Seder, says, what does the bad son ask? He asks, why is it that you did this? It must be that it's not hard, and so forth. That's the Fox Committee. But in any case, so say, no, that's not it. Irit is not happy with my portrayation. Anyway, so then no, actually there are actually instances that come out of Johann's reduction, the PCP reduction, where you can show that perturbation also will help. So it's not the fact that these are such a weird set of constraint satisfaction problems. Another question you ask, does correlation always help? And the answer is no and yes. No, we can show instances where it doesn't help. And yes, I'll explain in a minute why I say that in some sense I think it always helps. The third thing you can ask is, what about how much correlation? Or in some sense, correlation versus diversity. So it seems to be the case that in some sense, look, if you are completely correlated, right, that's not good enough. Like if you're the same, then it's no help. If you are independent of the other instance, also it's not going to be good enough. So, if you look at the techniques, this translates to something more technical, where we actually needed, in some sense, a difference between the instances in order to compute sort of a derivative according to which this function is changing. And if we had too much correlation, we won't be able to detect it, and too little correlation, we won't be able to find it. So you need. It's a non-monotonic behavior. I think it's an interesting behavior to study. When does it become too much correlation to be useful for our paradigm? Another thing is this the only place where correlation helps? And I say no. There's actually examples an example in learning that we worked out. There's an example for planted clique graphs where this is useful, and I believe there would be others. And then finally, I want to get to this question of why did I say that this paper is about why I talk to people? Okay, so we're going to get to that in a minute. So just, why did I say yes? Why did I say the correlation always helps? There is this beautiful result on randomized encoding by Applebaum, Ishai, and Kushilevitz, where they show that every function can be converted to another function that computes essentially the same thing, and it's as hard to invert as the original one, but where the function is local. So instead of doing a very complex computation, it's a whole bunch of small local computations. We can show that their reduction, you can take any function, transform into that form, now breaks immediately with even one more correlated instance. So in a sense, it's not the difficulty of inverting that computation that made correlation, so in other words, every function, regardless of how hard it is to solve, has a form which is amenable to correlation, which can be solved in this correlated model. Let's get to the end. So what does this have to do with collaboration and talking to each other? So the truth is that Irit and I started this because she was a visitor at MIT, and we said, okay, let's work on something. And we had to find an intersection. So we said, it would be interesting to find out, why do people benefit from working together? Okay, why do they even talk to each other? Why do they go to therapy? What is the point of going and talking to another person? You could simulate the whole thing yourself. Okay, so we wanted to find some kind of setting, some kind of model where you could actually prove that it's beneficial to talk to each other. And what does this have to do with my talk? So if you think about it, let's say that I'm Alice and I have an input. Okay, so there's Y, there's everything I know of myself, but there's a hidden variable that I'd like to find out, some inner self-discovery that I'm interested in. And we could think of this, that there's a function of the a hidden variable, which is the outside, so y is equal to f of x. Okay, x I don't know. And Irit, or Barbara holds y prime, which is a function of x prime. Okay, so she has her inner truth. Okay, but what she knows is y prime. So is there any point in the two of us talking to each other where it turns out that even if we just tell each other what we know about ourselves, so I tell her my y, she tells me her y prime, voila, we can discover our internal truth as long as we act like a constraint satisfaction problem, which, you know, I'm not sure how maybe. The thing is that, of course, this doesn't really answer the original question. It would be much more interesting to find a situation where you can prove that we need to talk to each other in a more complicated way, like in an interactive way. Not that I just tell her everything about me, but that we really have to interact in order to get some computational benefit. So this brings me to the end. I think we did show that it's useful. I think it is available often, these correlated instances, and I think it's useful to look for them in order to solve your problem. Most important, happy birthday, Dick, and thank you very much for everything.
Questions?
Actually, just a question, whether you have this paper available on the website?
This paper? Yes, it did appear somewhere. Even, I mean, Fox is not the only place. It appeared in ITCS last year, but I can send you. Yeah, so in the learning, in the learning, it's for learning parity with noise. So in learning theory, people have looked at correlated examples, where the examples are correlated. Here we want to say they're correlated concepts. So let's say the two concepts of the LPN, the two solutions are perturbations of each other. And you get examples of the first, so equations in the first solution, equations in the second solution, noisy equations, and now can you do better? And there is a noise threshold, I think 1 in n, where we can do better than any algorithm that's known.